Now I got to use the power rule. The derivative of x to the ninth is, whatever you said, 9x to the eighth, right? So I have 5 times the derivative of the variable part, 9x to the eighth, minus 4, okay, 4 times 3x squared, plus 2 times, what is the derivative of x? 2. Derivative of x. Oh, well, altogether, with the 2, you're saying? Yes. This is a 1, so is that what you meant by 2? You were correct, that's right. What is the derivative of 1? 0. Good, 0, because it's a constant. So now we have our final answer. We just multiply this out a little bit. 45 x to the 8th, which just knew from the beginning, minus 12x squared plus 2. That is the derivative of the original h. Okay? Again, this was the most drawn out you could possibly do it. Just to exhibit the rules. Anytime you do the polynomial, you want to do what we just did not in slow motion, right? Bring down the 9 is 45, you get lower by 1, it's an 8. Bring down the 3, it's 12, lower that, it's a 2. Bring down the 1, it's a 2, and this goes to x to the 0th, which is gone. X to the 0th is 1. Constant goes to 0, it's over, right? That's the way you want to do it.
It looks a lot like synthetic division where power drops. It looks like the first one. Do you see what I mean?
It is not. It is not like synthetic division. It's a happenstance that synthetic division you get a loss of a single power, and here you also get a loss of a single power. It's true, but I don't think the coincidence goes much beyond that.
I have a question.
Yep.
So for the last part where it's 1, it's 0 because
Because the derivative of a constant.
Okay.
Our first rule here, right? Always 0. Because this little piece here, this little 1 on the end, represents like I'm subtracting the function 1, and that thing has a 0 slope. So now with polynomials, you're ready at any stage to crush them immediately, right? F of x equals 4x to the 12th minus 85. What is the answer to the derivative? 48 x to the 11th, and that's it, right? Say again?
What are we talking about?
This little guy here. You have to take its derivative very quickly, which is the way you want to do it. You don't want to do all that mess there, right? 48 x to the 11th. Okay, are we holding with these rules so far?
do you have to put like an f prime 48x11?
You would want to do
Okay.
that. Yeah, you want to tell them, you have your choice, depending on the problem. They may tell you to use a particular picture. You have df dx, or you would use f prime x. Either one of those is your choice. And then you'd say, yes, equals 48 x to the 11th.
Okay.
And what you want to keep in mind is you have found the slope of the curve anywhere for the curve, right? You see the derivatives we're taking now are functions. This derivative is a function. It has an x in it. So if I want to know what the slope of the curve is for this thing at the number 1, I can plug 1 into this derivative and it will tell me the slope there. It'll be 48. Okay? That make sense? So if I wanted the slope of this curve at -1, I'm going to plug -1 into here and get out what number? -48. That will be the slope of the curve there.
Is that telling you say find the derivative? Not actually find the derivative, just find the derivative, so you plug the number in.
Well, this thing is called the derivative. It's called the derivative. It's called the derivative function. Derivative function.
Okay. Yeah.
Because it does tell you anywhere you want what the slope of the curve is. That's true. Yep. As opposed to derivative at a point.
And the derivative is it's a slope at a point.
It's slope of the point. That's right. That's right. Rate of change of the curve. That's right. I think there are a couple more rules in this section. What do I got here? You got e to the x. And one. Yeah, that's good. Okay, one more rule. The rule for the exponential function. And it has a particular base. We'll do any base later on. exponential function base e. Whatever. Okay. There's an irrational number called e, which is extremely important in mathematics. Just like pi is an irrational number, and it's very important for certain geometric properties, so too this thing is extremely important. And its most fundamental property is that if you make it the base to an exponential function, f of x equals e of x, right? If you know what that looks like, I think you guys had that in pre-calc, right? We talked about it a little bit already. So that function looks like this, for the most part. 1. Got that horizontal asymptote. Right? That look familiar?
Yeah.
All right. So what's so good about this function? Why is it better than 2 to the x and 5 to the x? So the reason now is because its derivative is itself, which is not the case with any other base. Its derivative is itself. Well, there had to be some function like that, right? He just happens to be it. It's like asking why I'm so good looking. I mean, somebody had to be. Right? Oh, jeez. Anyway. Okay, fine.
What?
Anyway. Yeah, so what this is really saying is, if you go here to 0, then at 0, when you plug 0 in, you get out the number 1. That's the height. Well, that height is the same as the slope itself. The slope there is the slope of 1. If you go over here to 1, then the height is e, right? But you know what? That's also the slope. The slope there is also e. That's what it's saying. The function value and the slope there are exactly the same thing. Oh, that's awesome, isn't it? Well, I'm glad there is such a thing, otherwise science would have been stymied for God knows how long if there wasn't such a thing. All right.
We should just take an average.
Say again?
Just take an average. So put all points. You put all these points on a curve, they're all relative to each other. So if they're 1, 2, 4, just draw tangent functions. You take those numbers and divide by the number of numbers you have, and you just take an average. It wouldn't be approximate. It wouldn't be like it would be approximate, but it wouldn't be exact. You see what I mean?
Well, it's either one or the other. It's either approximate or exact.
Approximate. It wouldn't be.
Yeah, it wouldn't be the thing itself. The limit makes it the thing itself.
Yeah.
Yeah.
So,
Why don't we just take the approximations?
Yeah, we'll just-
They did for a long time. They did. That's called the method of exhaustion. Basically. We got really close. Right? But it's the theory that gave us the exact. So now let's say you have a function like g of x equals 5e to the x plus 4x squared. Right? Some combination of polynomials and exponentials, which are the only things we know how to deal with at this moment, until the next few sections. So you want to take the derivative. I want to know the derivative of this crazy looking thing. So dg anyway, dg dx is going to be what?
5 plus 8x.
Sounds reasonable. Right? The derivative would apply itself to each of these separately, right? Because they're adding them together. So the derivative